Okay, we looked at the origin of the classical 20th century philosophies of mathematics, but now I want to take a longer view. I want to go back much further and also come more into the present. I gave this title, let's talk about some mathematics. I use some mathematics here to mean not mathematics in general. Don't just say mathematics and mean whatever you mean by it, but mathematics being done over in the math department now or at some other time at some specific place, specific mathematics by specified mathematicians. And here I'll talk about Athens around 430 BC, Plato's time, and Hippocrates of Chios squaring parts of the circle there. This is the earliest Greek mathematical proof we have. Columbus, Ohio, Amsterdam in the Netherlands, the last 40 years, incompleteness via interpretations, which of course is a specialty here on also. Princeton in the last 20 years, analysis and the idea of a function. What is a function? Including over at UCLA, Terry Tao on the best way to describe a function. And Zulip internet chat rooms. Zulip is a kind of chat room on the internet, and people are talking about computer proofs in these chat rooms. People are creating computer proofs by working in these chat rooms. And I would say dialogue opportunities between different philosophies of mathematics. Too often people who believe in some philosophy of mathematics only talk about that one instead of talking with other people who have different ideas about philosophy of mathematics. So by dialogue, I mean talking across two different philosophies of mathematics. This is an idea I owe to Sylvia de Toffoli in the conference that she had. I'll talk about people who study Frege, potentialist, structuralist, multiple reduction. Specifying who we're talking about, which mathematician, when they were working, what they did. This has a lot of advantages. It clarifies what we mean. If you just talk about mathematics, it's not always clear what you're talking about. By talking about specific mathematicians, you can see what I mean. For example, if I talk about Hilbert, people often say, well, David Hilbert, he was a structuralist mathematician. Even with Hilbert, he did many things over many decades. It would help if you would say which thing that he did you're talking about. People could tell more clearly what you mean. It puts the thesis at salutary risk. That is, it puts your claims at risk. It makes it possible for people to show you're wrong. But this is a good thing because then maybe they can't show you're wrong, right? I mean, if you express yourself very vaguely, no one can tell whether you're right or wrong. It's just not very interesting. So try to say things that maybe they're wrong and maybe you could show I'm wrong. Well, good, that would be a discussion. That would be progress. Did the person do what I'm claiming they did? And it makes philosophy of math fun. Math is fun. It's fun to learn some math. Especially if it's being done in interesting places like ancient Athens. It's just fun. Plato's character Socrates. Now, Socrates really did exist. He is a historical person, but we know him through Plato's writing, which is not historical writing. We know him as a character created by Plato. And he said 2,400 years ago, the character said, I think you know that students of geometry, calculation, and the like hypothesize the odd and the even. Now, what does hypothesize mean? That's a very serious question. That's not just a matter of looking the word up in a Greek dictionary. It's really a serious question what he means by hypothesize here. They hypothesize the odd, the even, the various figures, the three kinds of angles, the acute right triangle, oblique triangle, and other things akin to these in their investigations, regarding them as known. And these they treat as absolute hypotheses and do not think it necessary to give any argument for them. They just say what their hypotheses will be. They don't think it necessary to give any argument either to themselves or to others, as if they were evident to everyone. They just talk as if the way they're starting is obvious to everyone. And going from these principles through the remaining steps, they arrive in full agreement at the point they set out to reach in their investigation. They reach their conclusion from these steps. It's wonderful that we have this from 2,400 years ago. It addresses this. What does mathematics begin with? Philosophers of mathematics to this day disagree over what mathematics begins with. Does it begin with formal axioms? We say, well, there's lots of people did lots of stuff, but it's not mathematics until you have formal axioms. Some people want to take that attitude. Does it begin with mental constructions? Other people say, well, no. Well, mathematics is not about formal axioms. It's about things we create in our minds. Brouwer is very keen on this. Does it begin with empirical generalizations? Is mathematics a summary of, we say 2 + 2 = 4 because over and over again, if you had 2 cows and another 2 cows, you have 4 cows. If you had 2 bottles, another 2 bottles, you have 4 bottles. Is this just an empirical generalization? Some people argue that that's what math really is. Plato depicts mathematics around him as beginning with what the mathematicians literally say at the start of their lectures. They lay down hypotheses. But again, it's not obvious what that word means. It's genuinely not. You can't just look it up in a Greek dictionary, because Plato has a specific meaning. These hypotheses are not like the principles that Plato wants to find by dialectic. They are not established as true. Plato says by dialectic, we can discover what's the truth about beauty. We can discover the truth about justice by dialectic. We don't discover the truth of these hypotheses, he tells us. We just use them. They are taken as if they were true for the purpose of solving a problem. Elaine Landry has a short Cambridge Elements book out on Plato that I think handles this very, very well. So I recommend that. And Landry sharply distinguishes these from a foundation in the current philosophy of math sense of the term. This is not, for Plato, the mathematicians don't have a foundation for their mathematics. They don't have one set of hypotheses that everyone uses. No, at each talk, they lay down the hypotheses they will use in that talk. But this admits several different possible interpretations. It's not obvious what this means. Even if we suppose it's true, mathematicians only prove conditionals. They prove if this hypothesis, then that conclusion. Suppose we agree that's what the Greek mathematicians always did. They say, if this, here are my hypotheses, this conclusion follows. It remains to know, these hypotheses, are these things that could be established as true? He tells us the mathematicians don't establish them as true, but maybe there's things that could be established as true, or maybe there are things that could never be established as true or false. Or maybe there are things that are just known to be false. Option 1 leaves open, do these hypotheses, do they come from further mathematical investigation or something outside mathematics, like say physics? Maybe the geometers use hypotheses that you would have to go ask the astronomers whether they're true. You have to ask the people who study the stars whether these hypotheses are true, but the geometers use them. That could be the case. Or it could be the geometers use ideal lines that we know can never be real. It's entirely possible that most Greeks in Plato's time, they read a geometry book or went to a geometry lecture and they said, of course, this is an idealization. These aren't things that could ever be exactly true, but these are the idealization we use for mathematics. Or maybe they were things that were known to be false. And today, our fictionalists in philosophy of mathematics want to say mathematics is known to be false. They'll say mathematics says the set of real numbers is bigger than the set of natural numbers, but this is a fiction. There really isn't anything bigger than the set of natural numbers. So the fictionalists want to say mathematics is a series of literally false statements that are still interesting for various reasons. These are all possible interpretations of Plato. And I recommend it. Anybody who wants to go study Plato. We'll talk about Platonism in philosophy of mathematics as if people know what that is. but they don't know what it is, and they don't relate it to what Plato wrote. What Plato wrote raises very interesting open questions. And in particular, I want to relate it to a proof by Hippocrates of Chios. You may know there was a Greek physician named Hippocrates, different Hippocrates from a different island. That Hippocrates was from the island of Lesbos. This it's from the island of Chios, born the same year as Socrates, died maybe 410 BC, which is possibly when Plato's Republic is taking place. Plato wrote this famous dialogue, Republic, which I quoted from. Maybe that's the year that it supposedly takes place. It's the year of his death. Not the year he wrote it. He wrote it much later. And he was the first to write in Elements. You've heard of the Elements of Euclid? Euclid wrote Elements, the oldest surviving Greek geometry text. Hippocrates of Chios wrote an earlier one, which almost none of it survives. We have almost none of it today, but we have a little bit of it. Plato told us, we just saw, the mathematicians hypothesized the various figures, the three kinds of angles, etc., in each of their investigations. Well, if Hippocrates did that, that part's lost. We don't know if he did that. We don't have the beginning of his book, so we don't know how it began. Maybe it began like that. Plato says the mathematicians do begin like that. We don't know if he did. But here is the oldest known Greek proof. There were older ones. We've heard of older ones. The Greek historians tell us about older ones, but we don't have them anymore. This is the oldest one that we actually have. Let ABC let ABC be a semicircle. That's a semicircle. A DC is a quarter circle. What's the area inside that shape? Now, the Greeks, they wanted to be able to describe the area of a circle, and they did not have the formula for the area of a circle. They didn't have our concept of pi. They weren't really good at finding areas of curved figures. But Hippocrates is going to show you what the area of this figure is. They wanted to. The Greeks would have loved to be able to take a circle and draw a square of that same area. They couldn't do that. But Hippocrates says, take this area bounded by a semicircle and a quarter circle, that has the same area as the triangle ABC. That curved figure has the same area as the triangle. This was a big deal. We have a figure bounded by circles. It has the same area as a figure bounded by straight lines. They could not do the whole circle in a square, but they could do this thing. Hippocrates does this one. And we have a report of how it was proved. This report was written later, but Simplicius says he saw the manuscript. He saw the 200-year-old manuscript where Eudemus gave this proof. So he claims to know what the ancient proof was. And historians think it's likely to be true. We don't have Eudemus's proof anymore, but we have Simplicius's proof, report of it. Draw the right triangle, isosceles right triangle ABC. The segment on the base, that is ADC, that segment on the base, this segment here, equals the sum of the segments on the two sides. He doesn't say why, but this is the Pythagorean theorem. Now, Pythagorean theorem, we say this for squares. This is a right triangle because it's inscribed in a semicircle. The Greeks knew that. It's a right triangle. So if you take a figure on the hypotenuse, it has the area equal to the sum of the similar figures on the two sides. And Eudemus tells us that, Simplicius tells us Eudemus just said that. So if we take the curvilinear one, we take away the segments on the two sides, and then we add the segment on the hypotenuse, we get the triangle. So by taking equals away from equals, we get that the triangle has the same area as the curvilinear figure. That is the oldest Greek proof that we have. It obviously can't be the first Greek proof. It uses very sophisticated ideas. like that the figure on the hypotenuse is equal to the sum of the figures on the sides, but it's the oldest proof that we have to report it. Well, this is something other philosophers of math, you don't have to be interested in Greek math to talk about this. What about Frege and Kant scholars who want to say that for Frege or for Kant, mathematics is based on intuition? Can we talk about this proof as being based on intuition? Will that be interesting? I don't say they have to talk about this or otherwise their philosophy is no good. I say it would be interesting if they would talk about this. Can you explain this proof in terms of Frege's notion of intuition or Kant's notion of intuition? You certainly can't explain it by axioms because there's no evidence that Hippocrates had any axioms. Can you explain it by their notion of intuition? It's just meant to be an interesting question. It's not meant to be a challenge. You better do this or I'm not going to, it's an interesting question. Frege changed his mind about geometric intuition partway through his career. He gave it a much bigger part late in his career than he did early. Or does his later view make better sense of this argument? Again, it's meant to be a new angle, an interesting connection to make, not a challenge to Frege. So his early view, does that help? His later view, does that help? It'll be just interesting to know. I've read a bit of Frege. I've read things by Frege scholars, but I'm not specialized in Frege. And here's a question I have. Oh, I would be interested if they would talk about this. They don't have to. They don't have to write what I want, but I'd be interested. What about people, potentialists and modalists and Aristotelians, people who want to say that the Greeks didn't believe in infinity, but they only believed in potential infinity. They didn't believe lines go on forever. They just believed lines go on as long as you want. This result seems to use the Pythagorean theorem for circle segments. And the Pythagorean theorem, in general, requires the idea of parallels, and that requires lines that go on forever. To discuss parallels requires lines that go on forever. So by Euclid's time, Euclid was clear that meant the parallel postulate. Euclid probably gave the parallel postulate so that he could explain proofs like this. That seems to be historically true. Historians who specialize in this say that it's true. So that would be some kind of possible or potential infinity. But Aristotle tells us infinitely extended space is not possible, even potentially infinite. Aristotle tells us you can potentially infinitely divide a line. You can divide it in half, quarter, 1/8. You can, the line isn't already divided infinitely, but it's potentially divided. You can divide it as many. But he tells us that lines cannot even potentially be as long as you like. He tells us that lines have to have an upper bound. So if you think this proof uses a parallel postulate, you might wonder whether Aristotle should have a problem with it. Again, this is an interesting problem that I think Aristotelians might want to discuss. I'm not saying they have to answer it. But this might not be a problem for Hippocrates because Hippocrates doesn't give the general Pythagorean theorem. He only uses it on an isosceles right triangle. And that was proved. Plato, in one of his dialogues called the Meno, proves the Pythagorean theorem for isosceles right triangles. He gives the proof in the dialogue about 60 years after this other proof was apparently given. He proves it, he draws this diagram. He describes this diagram in the dialogue. So take the right triangle ABC. It's half of a square. But if you take the square on a line AC, that's 4 of those triangles. So the square on AC is equal to double the square on AB. Or if you like, it's equal to the square on AB plus the square on BC, but those are equal. So this did not talk about infinity. This special case that Hippocrates uses only talks about existence of squares, does not need parallel lines that go on forever without meeting. You just need to be able to inscribe a right triangle in a semicircle to give this proof. So maybe the Greeks thought this proof used less infinity than the proof that Euclid later gives. Euclid, it takes about 60 pages for Euclid to prove the Pythagorean theorem, whereas it takes one paragraph to prove this case of the Pythagorean. And Plato does write that paragraph. I'm not saying he could, he did. You can read it. Okay, for the structuralists, the anti-rem structuralists, what are these figures? The anti-rem structuralists say, well, mathematics deals with structures. Mathematicians use structures, but not just structures, they use systems. Systems are somehow more concrete than structures. A structure of three things is just three. They're not three of anything particular, they're just three. But a system of three things might be three particular people, or three particular rocks, or three of anything. And the structuralists say that that's a difference in mathematics between systems and structures. So how should we understand this mathematics is dealing with structures? Does anti-rem structuralism apply to this mathematics? Well, the existing text is too vague. There's no hope that you could actually answer that question from the text, but you could still say what difference it would make. You could say, what would Hippocrates have to say to decide whether he's dealing with a system or a structure? I would be interested to hear what people think about that, about anti-rem structuralism, what they think about it. And if the question doesn't apply, if you can say, oh, no, anti-rem structuralism, that's modern mathematics. It didn't apply to deal with Greek mathematics. Well, okay, when did it start to apply? How do you tell the mathematics it applies to from the mathematics it doesn't apply to? Now, this may be a very difficult, subtle question, but we could at least consider the question. Lots of historical questions are hard to answer. We're just in the Hubei Provincial Museum, and the exact nature of the, what was the Duke Yi's dynasty? Anyway, there are current discoveries revealing the exact history of the dynasties in Hubei. But you know what would count as evidence. You know how to interpret the evidence, even though you don't have as much evidence as you would like. Although in the last couple of years, they have much better evidence than they did. I'm not even sure whether the anti-rem structuralists think that mathematicians today distinguish systems from structures. That may just be something they do vaguely, or it may be something they don't do, but philosophers could do. I'm not sure the anti-rem structuralists all agree about this, and I'm not sure what any of them think about it. So it's just interesting to hear. Is this something that philosophers bring in? Okay. I'm not against philosophers bringing things in. Maybe philosophers introduce this distinction to understand what's going on better. But I would like to know which one the theory says. Does the theory say mathematicians make this distinction and we can learn from it? Or does the theory say we can go over to math and make this distinction? I'm not sure which one they're saying. Okay, another theme, interpretation and logic. Now, this is something of a specialty here with Professor Chung. So I'm still going to talk about Professor Chung here. So, Saul Pfefferman in 1960, people are familiar with Gödel's second incompleteness theorem. Peano arithmetic cannot prove its own consistency. And Peano arithmetic is consistent with the denial of its consistency. These are equivalent things. But Saul Pfefferman in 1960 already saw that this is a serious understatement. This says much less than the theorem is about, even if you only care about Peano arithmetic. Peano arithmetic cannot even interpret itself plus its consistency. And you might think, well, sure, because it would have to talk about itself, and theories can't talk about themselves, but that's not the answer. It can interpret itself plus deny its consistency. It can talk about itself. It can imagine a way that it could be false, but it cannot even imagine a way it could be true. This is much stronger And I want to say, well, Pfefferman is very proud of this version, and I want to say this is I was going to say the right version, but I was just reading your papers. I mean, there's not one right version, but this is a very good version of it. And this raises the question of interpretation in logic. The other thing that, of course, everyone knows, everyone who knows anything about Gödel's incompleteness knows, we say the incompleteness theorems hold for any theory that includes a certain amount of arithmetic, but it doesn't have to literally include that arithmetic. It only has to interpret that arithmetic. So, for example, Zermelo-Frankel set theory, it doesn't include any arithmetic. There are no primitives for a natural number for a successor, but it interprets arithmetic, and so of course the theorem applies to it. No one even wonders whether the theorem applies to it, because we really knew we never meant the theory has to include Peano arithmetic or Robinson arithmetic. We only meant it had to interpret those arithmetics. But I think a lot of philosophers who don't specialize in this don't understand that distinction, and they should. It's a good one. There's a Rothkainen expresses it well for an encyclopedia article. He writes in the Stanford Encyclopedia of Philosophy, when it is said that a certain amount of elementary arithmetic can be carried out within a system, what we mean is either the system is an axiomatizable extension of Q or that Q can be interpreted in it. Okay, that's fair. But the third line is redundant. There was no use to say that it's an extension of, because if it is an extension, then it certainly interprets, and interpreting was good enough. You could have just left that out. He put it in there. He put it in for good reason. Non-specialists are reading this encyclopedia. But even non-specialists should be told that third line adds nothing. Just, it doesn't belong. What matters is whether Q can be interpreted in the system. And then when he comes to the second incompleteness theorem, which is, of course, much more subtle, he uses parentheses inside parentheses. In a parenthetic remark, he says, in the case of, and then in another parentheses, the standard proofs of the second incompleteness theorem, substitute PRA for Q. PRA is dramatically stronger and more complicated than Q. What point was I going to make there? Yeah, and in fact, he doesn't need PRA to be included there. Here's what he needed to say. He needed to say no axiomatizable theory can interpret Q plus con of itself. That was the right statement. Forget PRA. Probably a lot of you don't know what PRA is. I didn't for a long time. It's a good theory, great theory, but you don't need it for a correct statement of G2. You just need no axiomatizable theory can interpret Q plus its own consistency. Now I'm cheating a little bit here because how to express con U is a research project right now. There is research going on what's the best way to express that for weak theories U. It's obvious for Peano arithmetic, but of course, the whole point of this statement is we're way below Peano. So this is much more general because we threw out the reference to PRA. It's stronger than you can't prove something about its consistency. Again, it says you can't even interpret that thing about its consistency, right? There are a lot of things I can't prove are true, but I can tell you how they could be true. Interpreting is like being able to say how it could be true. Proving is like showing it is true. And you don't need proving. It's already interpreting is impossible. So there's a lot of ambiguity. This is research stuff. Albert Fisser, I think, is doing a lot of this, and Professor trying to concentrating on G1, but still has raised this. This ambiguity has been around all along. This is not newly discovered problems. These are problems that when Gödel first gave this result in 1930 and 31, almost no one understood it. But the few people who did understand it understood that these were questions for the future. These were things that would need to be spelled out further. And they're still being spelled out further, not slowly, but it's hard. There's a lot to do here. They're being systematic, articulated, generalized, explored. This is current research, and I would say very nice research. I will also say something that I don't think are in the slides here. When I first became aware of this research and started reading it, I was amazed because when Albert Fisser writes about this, it's like reading other math books. You read earlier things on Gödel's theorem don't look like other mathematics at all. They're very, which is not to fault them. It's not the same math. It doesn't. But Fisser makes it look like other mathematics. It just it's just the modern understanding unifies this more with how other math is being done. Just on a level of I look at it and I think, oh, this looks like the books I'm used to reading, as opposed to older books on Gödel's theorem. There are various generalizations of interpretation. There's not just one thing that interpretation means here. It matters how you define consistency, and I raised some different ways you might define consistency. These matter a lot. It makes a difference to the theorems, and a lot of that I think is provisional. Fisser and Friedman will both say we can prove this version. We'd like to prove that version, but we don't have it yet. And we think some of this maybe even could be simplified more. They don't have final forms because this is still going on. But here I overstate slightly. Equiconsistent theories always interpret each other. If each theory, well, if we regard interinterpretable theories as materially the same, then the only difference between theories is their consistency strength. This is a very great overstatement of currently proved results, but it's a simplification of currently proved results. Currently, this is proved on various conditions. It's only for finite theories, finitely axiomatized theories, not for infinitely axiomatized theories. It's sequential cut-free equiconsistency provable in elementary function arithmetic. I won't go into what that means. It's fun to learn, but I won't do it. It really is fun to learn. The details are in flux. You read Fisser's papers, he keeps coming out with new ones, and because it's developing as we speak. The classic example, though, is not new. The classic example here goes back to Hilbert, 1897. David Hilbert, who doesn't like to think about it? David Hilbert's just good. No, he writes good stuff. And this is David Hilbert in 1897, so you know you're going to hear some good stuff. He gives axioms for elementary Euclidean plane geometry in his book, Foundations of Geometry. The point of this book is to show that not only can the axioms be interpreted in terms of coordinate plane geometry, like the XY plane you learned about in high school, but that coordinate plane geometry can be interpreted in the axioms also. Each of these can define the other. And along the way, he shows that it's interinterpretable with hyperbolic, non-Euclidean plane geometry. The axioms he gives for elementary Euclidean geometry can be reinterpreted as axioms for hyperbolic geometry. You do have to change the way you express things, but Euclidean geometry turns into hyperbolic geometry. Logically, not geometrically. They're geometrically quite different. But each can interpret the other, and they can both interpret the theory of a real closed field. Tarski made more precise in 1930 exactly what's going on here. Formal axioms for geometry can also be taken as formal axioms for a real field. And formal axioms for Euclidean geometry can be taken as formal axioms for hyperbolic. The formal axioms don't determine what they're about. They determine what they can be used to express, but they can be used to express many, many different things. There's not just one thing those formal axioms could be expressing. Now, Hilbert writes the book as if they're expressing Euclidean plane geometry. But he shows you could have taken them as expressing hyperbolic plane geometry. You could have taken them as expressing the theory of a real closed field. And that's important. That was important to his mathematical project. They're different presentations of the same theory in first order logic. Tarski made that much clearer in the 1930s. Formally, they're just different ways of interpreting the same first order theory. And what's worse, if you think it's a bad thing, I put that question mark on it. It's not really worse. It's not bad. It's just, it's more extreme. Extrapolating from what's proved so far, every equiconsistent theory is another form of that same theory. That is an overstatement. That is not quite right. Oh no, and now people are taking pictures and they won't take a picture of my words that it's not quite right. It's not quite right, but it's close to right. It's a challenge to explore what's actually going on there. No, by all means, take pictures, right? I will say interpretation in formal languages is a current, crucial, practical, and theoretical problem for computer math. This is something the computer mathematicians actually face. What makes a computerized program, what makes a computer program a verification of a natural language proof? Well, people go to a lot of trouble to make sure that program expresses this proof. But the principled standards that of showing what it means to say it expresses the same, this is a real problem. This is something that we need to explore. And because there's going to be more and more computer mathematics. That's perfectly clear. I'll talk some more later about what people say, but certainly there's going to be more of it. Computers are being used in all kinds of ways. So some beautiful work in fluid dynamics. You might think fluid dynamics, that's practically engineering. They're not going to use computer math. Well, they use for numerical approximations, but not just numerical approximations. Some of the cutting edge work now being done, actualizing some of it in China. You have a computer doing numerical approximations to these equations, but it's also designing what it will do next based on what it got so far. The computer is picking how to refine the estimate next time in a way that humans used to do. Humans used to say, well, print out what you got right now. Oh, maybe I'll have you do this next. They have the computer deciding what to do next, and it's working. It's giving very nice results. So that's something that looks very far from computer math, but it is computer math. How does a given piece of code express a desired human thought? What does it mean to say the code expresses a thought? How do you verify that the code expresses a certain thought? These are problems that computer scientists actually face when they're actually writing programs to verify specific proofs. Within philosophy, we have this multiple reduction problem. Say, well, what are the numbers? You might say zero, you say numbers are sets. So 0 is going to be the empty set. And 1 is going to be the set whose only element is the empty set. And 2 is going to be the set whose only element is the set whose only element is the empty set. And we get this bunch of sets. We say, these are what the numbers are. And then somebody comes along and says, no, I got a different way to do it. I want 2 to be the set whose 2 elements, 1 is the empty set, 1 is the set. So we get a different sequence of sets. Paul Vanastroff writes about this in What Numbers Can't Be, a paper people still cite now. How do we decide which sets are the natural numbers? I would urge you to not decide which sets are the natural numbers. If every natural number is some Zermelo-Frankel set, there's a big problem. Which set is 2? You have to decide which set is going to be 2. And there's no right answer. There's lots of answers that all work. They all work great. They're different from each other. But if you think that the number 2 has to be some Zermelo-Frankel set, you got to pick which one it is. You can't pick which one it is. It's a nonsense problem. But if natural numbers are defined by PA and just related to ZF by interpretation, there's no problem with there being multiple interpretations. Nobody says you have to tell me what the number 2 can be interpreted as. It can be interpreted as lots of things. There's no problem saying there's lots of ways you could. There is a big problem in saying there's lots of things it might be. If you think it is one of them, you should know which one. There's no problem about saying which it can be interpreted as. Of course it can be interpreted as lots of different things. I don't know if yeah, it's like saying it's a puzzle that there are multiple different parking spaces that suit my car. Of course there are lots of parking spaces that suit my car. If you're going to sell people parking spaces and each person owns one parking space, you got to decide who owns which one. But if you just want cars to be able to park there, there's lots of spaces that the car can park in. That's not a problem. Same thing here. If you're going to tell me that everything in mathematics is a Zermelo-Frankel set, then I need you to tell me which one is the number two. It's a nonsense question. If you're going to tell me that numbers can be interpreted in Zermelo-Frankel, yay, great, and can be interpreted lots of ways. That's not a problem. So would it be good? Would it be good to get rid of the multiple reductions problem? A lot of papers have been written on the multiple reductions problem, but I think, yeah, it would be good to get rid of it. Forget that problem. And can we relate this question to the Frege-Hilbert debate about which things are mathematical terms referring to? The Frege-Hilbert debate is a debate that Frege scholars talk about a lot. I won't go into it now, but can we use interpretations to shed new light on that debate? See, this does make proof theory look a lot more like other mathematics. You get clean-cut, uniformly expressed, motivated definitions. Albert's papers are full of these. There's a lot of definitions, but they're clear. They're motivated. You can see what they're for. You have theories themselves as structures mapping into each other by interpretations. Every other branch of mathematics talks about structures mapping into each other. Well, so does this branch on this approach. The definable types in a theory become structures mapping into each other by definable functional relations. Everybody does that, just not everybody makes it look as much like other mathematics as, say, Albert Visser does. My first trip to China, I was at Beijing for an international congress in logic, methodology, and philosophy of science. And I believe it was Ehud Rashevsky gave a talk on model theory. And he was explaining that modern model theory isn't necessarily what philosophers know about. In modern model theory, we take a model and we define, and then he looks down into a category of definable sets. He had to say category because it's true, but he knew that a lot of people in the audience didn't want to hear him say category. So he actually looks down and says, we define a category of definable sets. Yeah, it is. Don't worry about it. It's a category. Not a cause for concern. Because same as other branches of math use categories, this one does too. And then it parallels a trend in model theory where you do similar things. What about for foundations? Do we want to say that mutually interpretable foundations can do all the same things? Now here there's an important ambiguity between mutually interpretable and bi-interpretable. There's a lot yet to spell out here, but it's a problem that I think people in foundations should really be looking at. They should take an interest in this, and we'll see more reasons for that later. That does not mean that mutually interpretable foundations are equally good for all purposes. Absolutely, they are not equally good for all purposes. But it could forestall a lot of silly objections. People will say, well, categorical set theory can't do this or can't do that. It just can. It really can. It's mutually interpretable with Zermelo-Frankel, so it can do all the same things. That doesn't mean you have to like it, but it does mean they can do all the same things. So stop saying they can't do the same things. They can. And this brings us to something more recent, the function concept and analysis. Now, I'm talking about analysis, advanced calculus analysis. Working analysts actually all know the history of 17th through 19th century mathematicians, advancing from vague notions to the set theoretic idea of function. In the 17th century, people said, let the position of a violin string be a function of the length. And so a function might be a violin string plucked. It's been plucked out of place and you're going to let it go and it's going to vibrate. They're a very vague idea of function. Well, I won't go into that whole history now. What I will say is that when you read analysis books, they will talk about that history. In particular, Stein and Shakarchi, Elias Stein and Rami Shakarchi. Elias Stein, very distinguished analyst, professor of mathematics at Princeton. decides he's going to utterly remake the analysis sequence. He is going to change it from the ground up. And he gets a graduate student, Rami Shakarchi, to work on it with him. Rami Shakarchi later went into banking. Okay, well, that's a lot of money. And they wrote a 4-volume Princeton Lectures in Analysis. This is a fantastic series. I will compare it to the Feynman Lectures on Physics. It's that readable, it's that authoritative, it's that excellent. This is like the Feynman Lectures on Physics. And I'll tell you one way it's like the lectures is as I'd be reading and I'd be going through some subject, and sometimes I would start to think, okay, maybe I've learned enough about this subject for now. Maybe I could leap ahead to the next, I'll come back later, but maybe I'll leap that. And then they would change the subject in the next page anyway. They never beat anything into the ground. They say what they keep at it while it's interesting, and then they go on to the next topic. But they do this with expert judgment about what's important. Elias Stein, you cannot get more expert on analysis than Elias Stein. And they start with Fourier theory. Volume 1 starts with Fourier theory, which a lot of undergraduates never get Fourier theory. Math undergraduates never get Fourier theory. The engineering undergraduates do because they have to use it. But often the math undergraduates don't because it's considered a little too advanced, a little too arcane. But they start right out, Volume 1, Fourier theory, as Charles Fourier saw it in 1822. So 202 years ago now. And there's a lot you can't do with that. That naive version suggests a lot of things that it can't actually do. So in Volume 2, they add complex analysis, which can now do more of what it looked like, the promise that Fourier could not really live up to. And then Volume 3 introduces measurable functions to do even more. And it opens with a 1-page history of the set theoretic function concept. They don't just give the history in the preface and say, oh, here's where we came from. No, Volume 3 opens with the history of the set theoretic idea of function. Volume 4 comes back to that in the middle of the book. They're using this history of the set theoretic idea of function. The way they're using it is to show that the set theoretic idea of function is not now and has never been the most general notion of function in analysis. Any number of books and articles by philosophers will explain how set theory gave the current general definition of function, and that's what a function is. It's not true. The set theory gave the general set theoretic definition of a function, but it's never been the most general definition that the analysts used. And Stein and Shakarchi, they'll give the history and they'll say, okay, this is our official definition. Officially, what we mean by function is this thing that set theorists say. But we're going to talk as if, and then they go on and say they're going to say different things than that. They declare the practice we have already adopted not to distinguish two functions that agree almost everywhere. Well, set theoretically, if two functions for a function has a value at every point, but they're going to say, well, we got two functions, they differ at this point, we'll call them the same function. It's not the same set theoretic function, but they're going to do that. They informally, but constantly treat what are called measurable functions as real valued functions that simply have no determinate value at any single point. They not just might not lack a value somewhere, they have no determinate value at any single point. You can change the value at any single point. You can change the value at any countable number of points, and you haven't changed the function. This is completely false of set theoretic functions, but it's the way they handle. It's true of what mathematicians call measurable functions. Now, you can give a set theoretic foundation for measurable functions, but they won't be set theoretic functions. They'll be set theoretic equivalence classes of functions. But for them, for Stein and Shakarchi, they're functions. They say function, they mean what the set theorists would rather they call a measurable function, which is not a function. The functional analysis volume, informally but constantly, treats distributions as real valued functions with a striking property that they can contradict any value, finite or infinite, at crucial points. They can actually, the Dirac delta function. You may have seen the Dirac delta function. Lots of people have seen the Dirac delta function. I said Charles, Joseph Fourier in 1822 used an extraordinary function to solve differential equations. This is a function of x. You can see the q is a parameter. It's the variable of integration. X is a variable, and delta of x is going to be 1/2 pi times the integral from infinity to infinity of cosine of q times x dq. Other mathematicians looked at this, and most of them said that doesn't mean anything, which is true. You cannot make precise sense of this in terms of the Riemann integral or Lebesgue integral. This just makes no sense. If x is 0, this is the integral over the whole line of 1. 1 has no integral over the whole line. It goes off to infinity. If x is non-zero, as you take the integral farther and farther out the real line, it oscillates back and forth. It does not converge to anything. It keeps oscillating between 0 and 1, or depending on how you take. And so that's just not a sensible integral. But other people just calculated with it by the rules that Fourier gave, and they solved differential equations. They gave independently verifiable solutions to important differential equations, which had not been solved before, by calculating with this expression as if it was a function, when it's not a function. Today, differential equations textbooks define it by giving this integral rule. You may have seen this integral rule. It's pretty popular. You take any function you like from the reals to the reals. You integrate it against delta along the whole real line, and you get the value of that function at 0. Integrating any function g against delta gives you g at 0. Gilbert Strang has this wonderful textbook. It's just a calculus sequence textbook called Differential Equations in Linear Algebra. It's a really terrific book. He calls it by no means an ordinary function. This is sophomores taking a calculus class. He's not going into set theory. He's not going into logic. He's not going into foundations of math. He just says this is by no means an ordinary function. It contradicts any value you could give for delta of 0. No matter what value, finite or infinite, you give for delta 0, you will not get those integrals. For one thing, you can see that for any standard notion of integral, Lebesgue or Riemann integral, changing the value of the integrand at one point doesn't change anything. This is a standard theorem on Lebesgue and Riemann integrals. So let's just change the value of delta to be 0 at 0. Now it's the constant 0 function, and you certainly don't get that. The integral with every g would just be 0. So this is not a function. But these are used all over math, physics, engineering, research. This is undergraduates. Actually, I think undergraduates in physics and engineering more often meet the Dirac delta than undergraduates in math, but it's not rare in math either. People meet this. Now, philosophers like to talk about why mathematics succeeds, and they should like to. It's crazy how well mathematics succeeds. You've heard of Wigner's paper, The Unreasonable Effectiveness of Mathematics. Why does mathematics work so well in the sciences? When the physicists come up with quantum theory, they got all these weird behaviors. The earliest days of quantum mechanics, it's very and they go and they talk to their mathematician friends, and the mathematicians say, "Oh, that's the mathematics of integral equations." Hilbert and Courant had already written a 3-volume work on all the mathematics people needed for quantum mechanics in the 1930s. Now, that didn't solve the physics at all. No, this did not answer the physical questions. But the math, they delivered all the math you needed before anybody needed that math. Why did the stuff that Hilbert and Courant wrote just because they were curious about it, turned out to be exactly what Heisenberg and Schrodinger and Bohr needed in quantum mechanics. You may know the story of Einstein after he gives special relativity, and he says, oh, there's a problem here. In special relativity, no signal travels faster than the speed of light. But in all our standard gravitational theories, gravity immediately affects everything at arbitrary distance. So we're going to have to change the nature of gravity. And he spends years thinking, what am I going to have to say to combine gravity with special relativity? Special relativity was designed to work with electromagnetism, and it worked beautifully with electromagnetism. But they had this problem with gravity, that gravity seemed to send signals instantaneously. And so special relativity said you can't send signals instantaneously. So as Einstein, the more he's looking at it, the more he thinks, it's as if space and time are somehow bending or something. And he goes to his friend Marcel Grossman, and he says, Marcel, have you mathematicians, have you ever come up with an idea of like a space that bends inside itself? I don't mean it bends outside itself. Within itself, it bends. And Marcel Grossman says, oh, yes, Riemann did that. Bernard Riemann, one of our favorite guys, did that back in the 1850s. And this turns out to be exactly the mathematics Einstein needs to give general relativity. Again, the math didn't produce the general relativity, but the math general relativity needed was already there. And Riemann had already suspected maybe this has to do with gravity. But Riemann was talking about curvature of space, not space-time. Riemann didn't have an idea of space-time. Curvature of space alone will not explain gravity. But he said maybe this curvature has to do with gravity. Turned out to be exactly Riemann's curvature was what Einstein needed with space-time to give a general relativistic theory of gravity. Why does math do that? Why is math so successful? It really is kind of crazy. And here's an example of one of the places where it's a little bit crazy, is that this idea of Fourier's back in 1822, which was largely wrong. He says things about it that to this day are wrong. And the parts that aren't wrong just look to most of his friends as like nonsense. They weren't nonsense. They've been made to work. Stein and Shkarchi, there's no nonsense in Stein and Shkarchi's books. They show rigorously this works. You can put it all on standard set theoretic foundations. This stuff actually works. If you want to explain why mathematics succeeds, this would be a really good example to talk about. I mean, if you just want to prove math does succeed, your work is done. Math succeeds. But if you want to talk about why it succeeds, this is a great example to go into. There is already good historical work on it by Michael Barani. I just got that name in there. If you look into analysis, as I mentioned, Stein and Shkarchi have to use complex numbers. Now, Phrygians and structuralists, philosophers of mathematics, people in this kind of philosophy of math, often talk about explaining the complex numbers. Well, I think it would be good if they would look at what the Princeton lectures talk about here. For example, Frege has this relevance constraint. Frege wants to give a logical reconstruction of every concept in mathematics. And he wants that reconstruction to focus on the main application. What is the main purpose of this idea? So the main purpose of natural numbers is to count. He wants the definition of natural numbers to express counting things. There was never one main purpose for the complex numbers. I think if Frege had looked more deeply at the complex numbers, he'd had to say, there just isn't one main purpose. There are at least two main purposes. One is the algebraic role. Complex numbers mean that every n-degree polynomial has n roots. You have to count the complex roots for every fifth-degree polynomial to have 5 roots. You also have to count their multiplicity. So complex numbers were introduced to solve polynomials, but they were also introduced to model waves, to model oscillations. At the same time, before the algebra was worked out, Euler was using them to model oscillation, which is just a completely different thing from roots of polynomials. the complex numbers never had one single main use. They had two main uses right from the start. And this also means there is not one sense of isomorphism from the complex numbers themselves. Structuralist philosophers of mathematics far too often say that the structures of mathematics are only defined up to isomorphism. Any two isomorphic structures count as the same, as if there's only one thing isomorphism could mean. But there is not only one thing isomorphism can mean, even when you talk about isomorphism from the complex numbers to themselves. There are many different senses of isomorphism from the complex numbers to themselves that are all important. Algebraically, you might mean a field isomorphism. There are infinitely many field isomorphisms from the complex numbers to themselves, but there's only two that preserve the real numbers. Now, when philosophers talk about the complex numbers, they say complex conjugation is the only isomorphism they have to themselves. You take the I and reverse it with negative I. They'll say the complex numbers have one isomorphism to themselves. It's not the identity, namely complex conjugation. That is indeed the one algebraic isomorphism that preserves the real numbers. But algebraic isomorphisms don't need to preserve the real numbers. And algebraic isomorphisms aren't the only kind of isomorphism that mathematicians use. So this whole talk about structures being defined up to isomorphism already breaks down completely, even for the simple case of the complex numbers. And a structuralist can say, well, okay, this was all provisional. We're developing a theory here. Great, of course you develop a theory. André Weil told us that in developing new landscapes, it would be a terrible idea to be rigorous from the start. And he was going to argue with André Weil. But now maybe we could start to be more rigorous. Stop thinking that if you got structures, they might have a notion of isomorphism. If you've got structures, they probably have several notions of isomorphism. It's extremely important in complex analysis that every two complex elliptic curves are all isomorphic to each other as topological spaces. They are not all isomorphic to each other as complex manifolds. And this is crucial to all the applications of elliptic curves in mathematics. There's two different notions of isomorphism. In one sense, they're all isomorphic to each other. In another sense, there's a very complex family of isomorphism types. They're not all isomorphic. Both senses exist. And because both senses exist, mathematicians have standard ways of talking about them. But philosophers too often talk as if, nope, no, there's just isomorphism. It would be more interesting if people would, besides, like I say, they're nice books. They're nice books to read. There are about 6 important notions of isomorphism of the complex numbers to themselves that you will find in standard graduate textbooks. And the textbooks don't confuse them. The textbooks know absolutely what they're doing. They distinguish however many of them they use, and they distinguish their properties. There's no confusion about this in mathematics, but there's serious confusion about it in structuralist philosophy of mathematics. Terence Tao studied with Elias Stein in the 1990s. There's a connection here. Terence Tao wrote this textbook, Analysis 1, Analysis 2. If you've had a good course on analysis, you should read the Princeton lectures. They're great. But if you haven't yet had a good course on analysis, you should read these. These are beginners' books. And they're very nice books. The results are entirely classical. In fact, Tao, he even gives the classical order. Where Stein reordered the whole advanced analysis sequence, Tao just does the classical basic analysis sequence, but he does it with his own vision of the connecting line, his own vision of what motivates, what connects, what makes this comprehensible. You get his vision of that. And he actually, in other works, has urged a wider, more explicit generalization of the function concept than Stein did. Remember, Stein officially keeps the function, the set theoretic definition of function, and he only bends it in analysis. He talks other ways in analysis. But Tao is going to talk much more generally. Tao, again, these people are not confused. Tao says the set theoretic definition of function suits set theory. It is exactly the right definition for set theory, but set theory is not all of mathematics. He says, however, there are fields of mathematics where this may not be the best way of describing functions. In geometry, for instance, the fundamental property of a function is not necessarily how it acts on points, but rather how it pushes forward or pulls back objects that are more complicated than points. What does he mean by that? You can go read he doesn't give examples, he cites them. This is from the Princeton Companion to Mathematics, a lovely book, really terrific book. And he cites other articles in that book where you can go and read these geometric examples. They are largely algebraic geometry examples that matured under the Grothendieck school. Things that began, for example, with André Weil and Emmy Noether, but they reached their final polished form under Alexander Grothendieck. Those are actually the examples he's talking about there. And he refers elsewhere for them. But his examples from analysis go back to Euler. He also gives examples from Euler, and they are not 20th century. They are 18th century. They go back to Leonhard Euler. So not only historians, but also analysts know this. Edouard Bourassa, in his Cours d'analyse mathématique, he looked back 100 years ago. Writing in 1933, he talks about the modern definition of the word function. Because the modern definition of the word function is due to Cauchy and Riemann. One says y is a function of x, when to each value of x corresponds a value of y, when indicates this by the equality y equals f of x. This is what Bourassa says in the leading calculus textbook of the 1930s. And he refers back 100 years. Compare what Tao writes in his textbook in the 2010s. A function f of x from x to y is an operation which assigns each element or input in x as an element or output in y. It says the same thing, it's just slightly different words. It's really the exact same thing, just in slightly different words. So this definition has been stable. Cauchy and Riemann gave this in the 1830s. Actually, not a lot of people understood it. Even Cauchy and Riemann did not understand what it really meant. They didn't understand the full ramifications because set theory did not exist yet. People like Dedekind and Cantor invented set theory partly to understand what Cauchy and Riemann had said was a function, to get a clearer understanding of that. So Cauchy and Riemann, they do say it. They don't really understand it very well. Bourassa says that 100 years later, having learned set theory in the Dedekind, Cantor, Zermelo's sense, but even so, in 1930, the standards of rigor in math books were not as high as they are now. There was a lot of sloppy writing in math books. And now in 2010, with much higher standards of rigor, Tao gives the same definition. This is really the same definition, running for 200 years. But again, this is the notion specific to set theory. This is not the only notion. This is the notion for set theory. Okay, yeah, actually, I got these. Been through that. Oh, yeah. What can we say about the delta function? It's not just that equation. Textbooks today introduce the delta function as a function that's zero whenever t is not zero, and delta zero so high that the area under the graph is 1. So you can take this drawing. These are normal curves. Each one color is one curve. These are normal curves with a mean of 0. So the area under each one is 1, but narrower and narrower standard deviation. So they fall away from 0. They rise ever higher at 0. you can say that the Dirac delta function is the infinitely high narrow limit of these as they go to zero everywhere except zero and go to infinity at zero. But that's not a precise definition. You can give the integral equation. That's the same integral equation that we saw before. So you can use it, and you can make this precise the way Stein and Shikharchi do by using the idea of a topological vector space. That's a fairly sophisticated idea. That's an idea that only arose in the 1940s. And that Schwarz, what was Schwarz's first name? I've gone and forgotten what Schwarz's first name was. A Bourbaki member named Schwarz gave this definition in the 1940s. He was still spelling it out over the next decade. He took on a graduate student, Alexander Grothendieck. Grothendieck worked on some of this stuff. Anyway, we won't go into that. This function also has a derivative. You couldn't use this in analysis if it didn't relate to other analysis. It does relate to other analysis. In particular, it has a derivative. Now, this derivative cannot be defined by a limit of difference quotients, the way calculus classes define derivatives, because the function delta doesn't even have a value at zero. The function delta is zero everywhere except at zero. It has no value at zero. So it cannot be a limit of difference quotients. What is it? Well, it's a derivative in a symbolic sense because some, although not all, the familiar rules of calculus apply to it. That's the point. We're going to get the rules of calculus to apply to this thing. It's introduced by the same way delta t was introduced. We can motivate it in words, and we will. We can draw pictures, we will. And we can give an integral equation, which we will. In words, the derivative is zero when t is not zero. That makes sense because the function itself was zero when t is not zero. It was constant zero. Of course, its derivative is zero. It's just a constant function. So its derivative is zero. But when t approaches zero from the negative side, this function rockets up to infinity, then rockets back down, and then rockets back up to zero, and it's zero again is zero. This is not a set theoretic function. It's like this. It's the infinitely high narrow limit of these things. These are the derivatives of normal functions. Dirac delta was the infinitely high narrow limit of normal distributions. The derivative of the Dirac delta is the infinitely high narrow limit of their derivatives. So it goes like, say, it goes shooting up, it shoots up to infinity, back down again, back up. This is not a set theoretic function. That's just a picture. That picture is not. The integral equation says this. Take any function from the reals to the reals. Now we require that this function have a derivative at zero. Before, what we said before for any function, now it only works if it has a derivative of zero. If you integrate that against the derivative of the Dirac delta, you get the negative derivative of g. Why the negative derivative? Well, that makes integration by parts old symbolically. If you write integration by parts, it's going to work out. So this is the negative sign makes standard rules of calculus apply symbolically to this thing. This thing is made rigorous, again, not by the pictures, not by the words, and not just by the integral equation, but by talking about topological vector spaces. There's in functional analysis, there is a standard set theoretic foundation for this kind of thing. It's called a generalized function. It's called a Schwarz distribution. I can't believe I'm blanking on Schwarz's first name. And there's a standard set theory, but it uses a fairly complicated idea of infinite dimensional topological vector space. It just does. Many of the usual rules of calculus work for it. That's why it's useful. A lot of my work in philosophy of mathematics focused on category theory, And I wanted to show philosophers how category theory was affecting other math, notably algebraic geometry. And yet, this stuff, which comes out long after I did that work, this came out decades after I was in graduate school, is making the same point as I wanted to make there. I wanted to say, look, you should, as a philosopher of math, you absolutely need to know the history of set theory. You absolutely need to know the important successes of set theory. You need to know the important struggles of set theory. You need to know what it achieved, but you also need to know it's not the last word. Set theory is not the only way of organizing mathematics. Category theory has been. Set theory came out of the 19th century phase we talked about. Category theory came out of the 20th century phase we talked about. Hardly surprising that with each new century, you're going to get new ideas. And now in the 21st century, we see, okay, the reason I called this long view, it starts in the 18th century, but it continues into the 21st. We have this different view of functions. The set theoretic foundations for mathematics do not define mathematics. They serve mathematics. You can give a set theoretic definition for all of this. Stein and Shikharchi do in their exercises. If you want to know whether this is legitimate in terms of set theory, you can read Stein and Shikharchi's chapter on this thing, and they will show you how it makes sense set theoretically. But it's not going to be a function by the set theoretic sense. That doesn't change. The Dirac delta is not a function in the set theoretic sense. Measurable functions are not functions in the set theoretic sense. They just aren't. Yeah, actually, we had this. Yes. Tao goes on to describe the better way of describing functions. In analysis, it's helpful to think of the various notions of a function as forming a spectrum with very smooth classes of functions at one end and very rough ones at the other. By a smooth function, Tao means exactly what all textbooks in mathematics currently mean by a smooth function. He means a real valued function that has derivatives of all orders. That's a smooth function. If that function is also the limit of its Taylor series, which not every smooth function is, but if it is, then he calls it very smooth. A very smooth function has derivatives of all orders, and its derivatives can be gotten by taking derivatives of its Taylor series term by term. It's what we call an analytic function often. What if you have a function, maybe it doesn't have a derivative everywhere. It's continuous, but doesn't have a derivative everywhere. He calls that a little bit rougher. That's rougher. It's a continuous function, maybe it doesn't have derivatives. That's rougher. What if it's discontinuous? A discontinuous but well-defined function is even rougher. And then you get things like the Dirac delta, which are not set theoretically functions at all. And then you get further things in that direction. Those are rougher and rougher. For him, they're all notions of function, but they're rougher and rougher. And half of that spectrum is not set theoretically functions at all. Yeah. Borel measures, distributions, hyperfunctions, Lagrange forms. Less. A sequence of smooth functions can converge to a rougher limit. This is obvious. You can have a smooth function like this, or a smooth function that's got more of a sharp bend, or even sharper bend, until you get the absolute value function that has a kink there. The absolute value function is a limit of smooth functions. So a smooth function can converge to a rougher limit, but this is extremely important. Okay, intuitively, a series of smooth curves with tighter and tighter bends in the middle might have a limit with a sharp kink, like the absolute value function. If you're an engineer will often approximate the absolute value function with a little U-shaped curve at the bottom because it's easier for the computer to deal with. A sequence of smooth approximate solutions to some differential equation may converge to a rough solution. Maybe you got a differential equation, for example, the three-dimensional Navier-Stokes equation. Navier-Stokes is a partial differential equation that just expresses Newton's law, F equals ma, for the flow of a viscous fluid. I mean, in engineering problems, in aerodynamics, in designing ships, you're constantly trying to predict fluid motion, right? I mean, you know, when they design these huge ships for sailing across the oceans, they do very careful mathematical analysis of how the water is going to flow past that ship, because any little gain in efficiency is going to mean millions of dollars worth of fuel over a couple of years. So they want to model how that fluid is going to move. They use the Navier-Stokes equation as the basis for that modeling. They do not actually use the Navier-Stokes equation itself in the model because the math is too hard. It's not feasible. You can't make it work. But they use mathematics motivated by the Navier-Stokes equation because that's the right description of matter. So it remains a very important equation. You can win $1 million by proving or refuting the claim that the three-dimensional Navier-Stokes has smooth global solutions for all initial conditions. It is not currently known whether the Navier-Stokes equation actually has non-trivial solutions. You feel like this is the right description, term by term, this differential equation makes perfect sense. Do the solutions match reality? We don't have non-trivial solutions. Currently, we can't come up with non-trivial solutions. So we don't know. We don't know if it even has solutions for many realistic initial conditions. If you can prove that it does have a solution for every smooth initial condition, you get $1 million. Well, you have to convince people you proved it, not if you think you proved it. If you can show a counterexample, if you can prove there's some initial conditions where smooth initial conditions where it doesn't have a smooth global solution, you get the $1 million. It's one of the Clay Memorial problem, the Clay Institute problems. It's a terrific problem. The current work is heavily based on Jean Larrey's 1935 proof that the 3D Navier-Stokes equation does have solutions for all initial conditions if you allow generalized functions as solutions. Jean Larrey in 1935 showed, yes, for any initial conditions, there's a solution if you will allow generalized functions as solutions. And this is the basis for most of the research going on the problem now. Now, his solutions, are his solutions smooth functions? We don't know. It's not that we know they aren't. We don't know they aren't. We just don't know whether they are or not. It's really hard to work in this field. Maybe he already gave smooth solutions for most initial conditions, but we don't know. He gave a solution that might not be smooth, that might be rough. So I'll say he solved Navier-Stokes in Fourier's sense by using the kind of math that Fourier was using in 1822, when a lot of his friends said, no, that's crazy, that doesn't make sense. And he said, no, it's not crazy, it doesn't make sense. We've now solved Navier-Stokes in that sense. Jean Larrey did it. And it's beautiful mathematics. It's very subtle. It's not some triviality, no. Larrey took advantage of two facts. One is there are more functions in Fourier's sense than there are smooth functions, just like there are more real numbers than rational. There's just more of them, so it's easier to find a solution. But more importantly, the spaces of Fourier's functions have nicer topological properties than smooth spaces of smooth functions. Just like you can do calculus on the real line, you cannot do calculus on the rational line because the real line has a continuous topology and the rational line does not. So you can do calculus on the reals, not the rationals. You can find Larrey's solution for Fourier's functions where you cannot yet find it for smooth functions. And that's a very close analogy. That's really to the point. Larrey shows for every initial condition for the 3D Navier-Stokes, there are arbitrarily close approximate smooth solutions. Those are smooth solutions. They're approximate smooth solutions. How close an approximation? You can't tell. Okay, so it's a problem for engineers. That doesn't make it easy. They don't just say, well, I'll take an approximate solution. You can't tell how close an approximation is. You can't find the very close solutions actually, but they exist. Leray shows they exist. He shows that some series of those approximations must converge to a function in Fourier's sense. Some series of them converges, not to maybe to a real function. You can't prove it's not a real function, but you can't currently prove it is a real one either. You can prove it's a function in Fourier's sense. The series might not be unique. We might not be able to actually find it. It might not converge to any set theoretic function, but it exists and it converges to a solution in Fourier's sense. This is, from a theoretical point of view, the sweetest known fact on the three-dimensional Navier-Stokes theorem. Now, if you're a real hands-on analyst, if you love complicated calculations and analysis, there's a whole lot known about complicated partial solutions to the Navier-Stokes equation. And then they're described in a beautiful book by Lemerrier called Navier-Stokes in the 21st Century. But the nicest theoretical result is Leray's here. Yes, the three-dimensional Navier-Stokes always has solutions in this Fourier sense. So we come to Luzin, a Russian set theorist in the 1930s, translated by Abe Schenitzer in 1998. At present, the concept of function is not as finally crystallized and undeniably established as it seemed at one time in the end of the 19th century. It is no exaggeration to say that a present function concept is still evolving, and the controversy about the vibrating string continues. Philosophers of mathematics do not know this. Most philosophers of mathematics believe exactly what Luzin is criticizing here. They believe the concept of function was finally defined in the late 19th century. Done. There's been no controversy since then. They are not aware of the mathematics that Luzin knew. Luzin correctly knew. He's saying, no, it's still going on. There's still these controversies in the 1930s. Well, the evolution is still going on today, but it's no longer controversial. There's no controversy about what is a function. New concepts are constantly developed, which are not function set theoretically, but are at least informally called functions. And nobody has a problem with this so far as I know. New ones, they are still being developed. They aren't function set theoretically. People call them functions. We just know it's not in a set theoretic sense. And I think philosophers of mathematics, Penelope Matty has her books on set theory tend to begin by showing how set theory gave the final definition of function. Boom, that's the end of that. We know what a function is. Now, her book does not only say that. Her book has a lot more in it than that, but that claim is not true. That did not stabilize the definition of function. It stabilized the set theoretic definition of function, but that's not the only definition people use. I don't know any mathematician who objects to talking about the Dirac delta function. Lots of math books say we shouldn't really call it a function. It's not really a function, but they do call it a function. They keep calling it that. They just say, honestly, we shouldn't. I don't know anybody who says, yeah, you got to stop. I just don't know anybody who says that. I don't know anybody who says you got to stop calling measurable functions because they're not. You just say, be clear, if you're talking about measurable functions, you're not talking about set theoretic functions, and you can't say the same things. And analysts are clear, and they don't say the same things about both. Analysts are never confused about this today, but they don't follow set theoretic usage. No one complains that the set theoretic definition of function is too narrow for the purposes of set theory, not even category theorists. We have a reputation for being difficult to please and always complaining about things. Nobody says it's too narrow, by all means. That's the definition of function to use in set theory. It's the definition we use in the category of sets. It would be a shame to make that the definition you use in the category of differentiable manifolds. But in sets, yes, absolutely. That's the one to use in sets. There's just a difference in practice over what is a function outside of set theory. The Princeton lectures on analysis very officially explicitly keep the set theoretic definition of function, but they also explicitly violate it in their language. They don't distinguish two functions that agree almost everywhere. They keep the official definition, and then they talk differently. They're explicit enough to preserve rigor. There is no sloppiness in those lectures. That's one of the brilliant things about them. Very sure hand at being rigorously precise without going to a lot of trouble to do it. They don't keep pausing and saying, well, to be precise. No, no, no. They make it natural. But they will say function f. They over and over again, they'll talk about a function f, where a set theorist would rather they say a class of functions equal to f almost everywhere. They will confuse a function with an equivalence class of functions. They are masterful, elegant. This is a beautiful introduction to why you would want to do math that way. Why would you want to talk about functions that don't have specific values anywhere? You're going to talk about their typical behavior without them having any exact behavior at any point. Why would you do that? Well, I don't have time to tell you why, but Stein and Shikachi do. They've got a great 4 volumes telling you why. This is the way to do analysis. And Tao builds up to it nicely. I mean, his analysis book is more elementary, but his contributions to the Princeton Companion on Mathematics, where he takes a more advanced viewpoint, he shows you how not only that this spectrum of smoother to rougher functions makes sense, but what sense it makes for particular problems, why you really want to have this whole spectrum. Sometimes work here, but sometimes work here, and sometimes work there. It's really good at showing you exactly why you would want that. He writes more explicitly about functions that are not set theoretic functions. He says a function space is a normed space X, it's a kind of vector space, the elements of which are functions with some fixed domain and range. He says that. It's a space whose elements are functions. Now, a lot of his examples, the elements are not set theoretically functions. For some of his examples, the elements are set theoretically functions. But for many of the others, they aren't set theoretically functions, but they are on his spectrum, the smoothness spectrum of notions of function. He gets the set theory right. Essentially, everybody working in mathematics today gets set theory right. Nobody messes up set theory. It's been too helpful in clarifying mathematics to go messing it up. Tao gets this in. And in fact, he is more careful with set theory. His analysis textbook introduces a new set theory, a new set of axioms for set theory that he thinks will be more helpful for his students than the standard axioms. He gets the set theory right with an expertly light touch. He never labors it. He knows, of course, every time I say he never labors it, I think that's what we philosophers do for a living. We labor things. We talk and talk and talk about it. He doesn't, he gets it quickly. Gets it right very quickly, easily. By not treating the set theoretic notion of function as the only notion, set theory becomes a help rather than a hindrance in the analytic insights that got measurable functions and generalized functions and more called functions in the first place. There's a reason why analysts since 1822 have been talking about these things as functions. They have good reasons for calling them functions, and Tao will help you learn those reasons without confusing you about set theory. Great, the set theoretic definition is one special case, but this more general usage will help you to understand the last 200 years of analysis, why it was done the way it was, and it's great stuff. Okay. In terms of structuralism, here's something maybe the anti-around structuralisms would want to look at this. Structuralists look at this and say, if you're going to say that mathematicians deal with structures, what does Tao have to say about that? Because the structuralists often say they have structures and structure-preserving functions. But Tao already knows that the morphisms in a lot of mathematics are not functions. They're not structure preserving functions. They're more complicated than functions. Well, he's correct, absolutely correct. And Bourbaki already knew this in 1935, that structures don't just come with structure preserving functions. If you're going to try to relate structures by functions, it's going to have to be more complicated than structure preserving functions. And again, the structuralists can say, well, come on, this is preliminary. We're developing a theory here. Great, great. Okay, but now it's time to go ahead and admit that that wasn't what mathematicians are doing. Go and get more specific about functions. This is, I would like to see the structuralists talk about this. And here's part of why I wish people would give more named examples. When people say Hilbert's math is structural, I want to know which math. His book on integral equations? No, the book on integral equations with Courant, that is just not structural. His book on foundations of geometry, now that's structural in some senses. His algebra is structural in other senses. Hilbert, the relation of Hilbert to structuralism is far more interesting than has been discussed so far by philosophers of mathematics. So because he has some, I mean, Hilbert has a productive career spanning 50 years. It's not surprising that he does different things at different times. It's wonderful how many different things he does at different times. But yeah, when you're going to say Hilbert is structural, he's, at the very least, we would have to say he does this different ways in different decades of his career. And here we come back to Hermann Weyl, who's been mentioned before. See, we've got three mathematicians here. We've got Hermann Weyl, André Weil, and Andrew Wiles. They're really all the same name. They're just different histories of the same word. Hermann Weyl actually has a biography of Hilbert. It's just a 40-page biography. It's not a 400-page. He's got a 40-page biography of Hilbert, where he breaks down Hilbert's work by decade, and you see the progression, different ideas in different decades, and they relate differently to structuralism. I think structuralism as a philosophy of mathematics would be way ahead if more people, not everybody in there, but more people there, would study the different things Hilbert did that were structural. You just understand more. Hilbert makes very little use of isomorphism or even homomorphisms. Tau analysis 1 gives an original axiomatic set theory designed to make set theory help. He says, I've given this set theory because I think it will help my students understand. Okay, if you believe in set theoretic foundations for mathematics, you might want to look at what Tau thinks is a more helpful set theory for students in analysis 1 and analysis 2. He's got a specific goal, which he thinks is better served by the slightly variant set theory. Is he right? What is working and what's not working in this set theory? Valuable topic to discuss. He notes his theory and ZFC can interpret each other, but certainly lots of things. And this brings us finally to computer proofs. Tim Gowers, there's supposed to be a picture of Tim Gowers there. Have you seen Tim Gowers? He looks like a sculptor. He's a very dramatic looking guy. He says in one article, I expect computers to be better than humans at proving theorems in 2099. Oh, we could wait and see. I probably will not get to wait and see. 2099, that's no, probably, yeah, that's too long. We can't be waiting until 2099. This is better. A lot of people predict things like in 10 years, computers will be responsible for most mathematics. That kind of prediction gets you in the newspapers, but the problem is that 10 years is not that long. And eventually it's 10 years later and people say, well, it didn't happen. What were you talking about? Gowers, he covered on that because 2099, we're not going to do it. We could just wait to see, but there have been diverse philosophic efforts. There are philosophers working on this very thing. There are mathematicians working on this very thing. Jeremy Abogad and Steve Audi at Carnegie Mellon, both philosophers. have been talking about computer-assisted proofs for a long time. There's just recently a 2-volume special issue of the Bulletin of the American Mathematical Society. The 2 most recent issues of the Bulletin of the American Mathematical Society are all about computer proof in mathematics. I have an article in there. There's articles by people who are doing computer proof. There's articles by people who are skeptical of computer proof. There's articles by people who think computer proof will take over. There's articles from various perspectives. I do have to say, whenever you talk about computer proof in mathematics, you have to know that there are billions of dollars of budget behind computer proof, and there is no budget for criticism of computer proof. So there's a whole lot of money urging computer proof. And of course, nobody's against computer proof. Nobody is saying, don't let computers prove mathematics. There are some of us saying that some of these predictions are overly optimistic. But the money is all on the computer side. Harvard recently got a $500 million grant to promote artificial intelligence. $500 million to Harvard. One of my friends was saying, well, I don't know what schools got it. Maybe what schools? It's a $500 million. Lots of schools got some of it. And it's not the only grant Harvard is getting to promote AI. On the other hand, it is genuinely big stuff. It obviously is genuinely big stuff. I was co-authoring an article on philosophy of mathematics in Chinese with Professor Liu Jie at Shanxi. I do not write in Chinese. No. She would write it in Chinese. She would send it to me. I would put it on Google Translate, right? I do not try to read Chinese just by glancing at the page. I put it on Google Translate, and then I would check the parts that I thought that I was concerned with, And we were doing this at the time that Google switched from their original algorithm for translating. Google Translate switched from their original to their deep learning model. And the day they switched to the deep learning model, the translations got obviously better. They got more natural and more accurate. At the same time, they were just, I'm a huge fan of computer translation. Well, as you know, I'm walking around the street now. I tried to buy a fruit knife. I wanted to buy a fruit knife to cut watermelon with. The way I finally bought a fruit knife was somebody held up her cell phone, and I said, I want to buy a fruit knife. And it said, it comes up with the Chinese. Machine translate is, of course you shouldn't do it instead of learning other languages. But life is too short to not use it. You have to use Google Translate. So there have been recent practical successes. Let's see, do I describe this one? Peter Schultz is a Fields Medal mathematician. He's developing a new approach to topology that he calls condensed mathematics. And for this, he proved what he calls the liquid tensor theorem. It's a theorem he was very proud of. It took him a year to give the proof of the liquid tensor theorem. And at the end of the year, you can imagine, he's working on this pretty much alone, and he's thinking, am I right? And so a little bit after he published it, he called some friends who were teaching that theorem in graduate seminars. And he said, do your students understand the proof? Everybody he called said, oh, we're not reading the proof. Nobody can understand it. So, so he calls Kevin Buzzard and says, you've got this computer proof assistant. Can that proof assistant help with the proof of the liquid tensor theorem? Can we do that? And they set up what they call the liquid tensor experiment. I have a team of like 12 people work on this for 9 months, and they get a computerized proof of the theorem. I don't think of it. Yeah. Schultz says, sometimes it was not clear how to proceed. The issue was raised in chat, usually quickly resolved. They worked together on this for 9 months. It's not just that somebody wrote a program. They worked together. After a lemma was entirely formalized, the proof thoroughly digested, was again written up in the blueprint in human readable form. I think here we have witnessed an experiment where the proof assistant actually assisted in understanding the proof. I will say that Peter Schultz has said he might not do this again. This, as I mentioned, this is like 12 people working for 9 months. Now, did they need a computer? If 12 people had worked on that proof for 9 months just in English, they would have improved it also, right? Was it crucial that this was on computer? And of course, the answer to that is we're not claiming that this was the best way to improve that proof. We're claiming that once this technology exists, we can apply it to all proofs. We're developing a new technology here. Of course, the first gasoline cars were kind of hard to maintain, but eventually they got easy to maintain because a lot of people had them. The current take home about this is going to be that in homotopy type theory and the liquid tensor experiment, you had teams of mathematician programmers collaborating for many months in Zulip chat rooms. This is just a kind of chat room you can go into online, and they're talking to each other. And these chat rooms are adapted to including computer code. So you can very easily put computer code in there, and it'll come out the other end as computer code, so people can work with it. And both of them, they didn't just have a target theorem, they both had a human proof of it. These computers did not discover proofs of the theorems. They developed proofs of the theorems in constant interaction with people who were using a proof they already had. So that's why Schultz calls it a proof assistant. It's not a prover. It's a proof assistant. It helps you understand your proof. So far, in those cases, the computers are not replacing human mathematicians at all. They're employing a team of human mathematicians. But in both cases, they did make people more confident of the proof. The computer, they produced a cleaner, more comprehensible, more confident proof by using the computer. In Schultz's case, they did discover small mistakes that humans would not have discovered, but the machine did discover. So these are really helping. So far, they are not replacing human mathematicians, but that's so far they're not. But can we think about Gowers' 2099? What will be happening in 2099? Or 2029? I mean, these things they're here and they are changing. One topic here for philosophers about computer proof, there's a Mizar proof assistant. This is one of the older proof assistants, and a lot of philosophers of logic are using proof assistants to create proofs in logic, but they're using the older ones. They are not using they're not using Lean, they're not using homotopy type theory. The Mizar proof assistant uses a variant of Zermelo-Fraenkel set theory that adds a lot of Grothendieck universes. I will say in my career, some people were very critical when I claimed that some people use Grothendieck universes. Well, a lot of these proof assistants have Grothendieck universes built in. They're just built in. You can't deny it. They're in the code. But essentially, all the others use type theories. Mizar is pretty much the only proof assistant that uses a variant of Zermelo-Fraenkel. The others use type theories, and the currently successful ones use dependent type theories. A dependent type is a family of types parameterized over a base type where the types in the family and the base type, it's complicated. It really is. It works great. It works great. I will not explain here what a dependent type theory is. You can go online. You can read lovely explanations of it. It came from geometry before computer science, and a lot of it was developed at Princeton using fiber bundles. Sharon of Sharon-Simons, Grothendieck Green-Rock. Will it turn out that math isn't set theory at all, but it's a dependent type theory? For all these years, my friends saying that category theory stuff, it works, but math is really Zermelo-Fraenkel. Really, math is Zermelo-Fraenkel. That's where the real math is. Are they going to have to change their mind and say, no, it's dependent type theory? I will say no, please do not. You shouldn't have said that math was really Zermelo-Fraenkel in the first place. Math is really math, and Zermelo-Fraenkel works for it, but so do other things. Currently dependent type theories work for it. Math is math. Analysis really is about analysis. It's not about the set theoretic definition of function. Algebraic geometry really is geometry. It's not about the set theoretic definition of function. But if you're going to tell me, okay, mathematicians, when they prove a theorem, they don't give a fully rigorous proof, but they believe it's rigorous as long as you could translate it into Zermelo-Fraenkel. That's why Zermelo-Fraenkel is the gold standard. Mathematicians believe a proof when you can translate it. Well, not anymore. Now they believe the proof when you can translate it into lean. And they actually do translate proofs into lean. It's not just they would believe it if, they do translate them into lean. So if you used to say math is really Zermelo-Fraenkel, maybe you need to start saying it's really lean. But maybe that sounds silly to you. You'd be right. You should never have said it was really Zermelo-Fraenkel either. It was really analysis and geometry and arithmetic, which could be expressed in Zermelo-Fraenkel, which could be interpreted in Zermelo-Fraenkel. Going back to interpretation. So here's a bunch of stuff that philosophers of math could all be talking about. And I think it would be a lot more, philosophy of math would be a lot more fun if more people were talking. Thanks.